Well, of all the speakers here, I'm embarrassed to say that probably I knew Professor Alvarez the least. In fact, it's uncomfortable for me to call him Louis, but I'll do my best. I came to Berkeley 20 years ago, and most of what I know about Alvarez I learned from Rich Muller. On the other hand, I was at Berkeley as a student, and I met him then, and I'll tell you about that. And the other thing I find ironic is that, as Rich is constantly pointing out, a lot of the problems I've taken on in physics have his fingers in it somewhere, and that's been constantly pointed out to me, mostly by Rich. After 20 years, I have to say that some of the stories he's told me more than once, but as we grow older together, I tend to forget them. So, I'm really here because of this chair, the Luis Alvarez Memorial Chair in Experimental Physics. And as I understand it, this was an initiative by Walter Alvarez and Rich Muller. It's a chair that's given with these rules. For 5 years, you get some research support that's, of course, usually very welcome, and that you're allowed to use the title of Alvarez Chair for Life. And one of the things that was mentioned is that Louis was fond of making recommendations and nominations, and having this next year title on your stationery when you're doing that is a great benefit. So this is one of the advantages of this particular honor. The first chair was John Clark, who probably most of you know. I was the second, and the third was Carlos Bustamante, a biophysicist, and you see that there's another young biophysicist now who is the present holder of the active chair. I'll tell you a little bit about how the financial benefits helped me. At the time I got this stipend, we were trying to get this experiment going in the United States. It's a neutrino experiment. It measures neutrinos from reactors in Japan, fewer reactors now than before, but this was meant to measure neutrino oscillations, and it did. And let me just show you one result that I particularly like about it. We now know that neutrinos have mass, and that the neutrinos that we used to talk about, the electron neutrino, the muon neutrino, and the tau neutrino, are linear superpositions in the quantum mechanical sense of different mass states. And so if you think about it, since they have mass, you can do this. If you sat in the rest frame of a neutrino, you would watch it changing from, say, an electron neutrino to some other kind of neutrino. And this is the data from the experiment that shows that effect. When these numbers are high, close to 1, the neutrino is an electron-type neutrino. And what's plotted here is not really the rest frame proper time, but it's a surrogate for that. And you're seeing the oscillation in proper time of the neutrino's name in its rest frame as they come from these reactors. This experiment helped resolve a problem that had existed since the early 60s. This was called the solar neutrino problem. It was caused primarily by this guy, Ray Davis, who carried out an experiment to measure neutrinos from the sun with the original intention of seeing how the sun works. Louis Alvarez was the first person to observe orbital electron capture, a process directly related to beta decay. I read his papers some years ago. They're marvelous papers. This process is very hard to measure, and it was almost heroic to take it on. In the final state, there's just a neutrino. There's no charged particles. And what he realized is that you could see it if X-rays were also emitted from the atomic conversion. And he was the first to verify that. That's the process that's used in this experiment to measure the radioactive argon-37 produced by neutrinos from the sun that capture in this tank of 650 tons of cleaning fluid. Now, Rich pointed out to me one time a paper in which Alvarez worked out this experiment. I don't know if he did it first. That really doesn't matter. He was one of a group of might have consisted of 4 or 5 people at the time who believed this was possible and important enough to do. Davis was one of them too, but this was a massive undertaking, pulling out a few atoms a week out of this tank of 650 tons of material. And it turns out it was absolutely true and proved what's called the solar neutrino problem. When I was a student here from the early 60s. I left in 72. I knew about the work at the Hill. This was big science. I thought it was interesting to see the results, but I didn't want to have anything to do about it. I instead believed that scientists should work alone in their laboratories. I do remember when I was here some events, some of which we talked about. This was a colloquium that was given around 1970. I can't really remember the dates. Louis Alvarez gave a talk on his analyses of the Kennedy assassination. The thing I remember about it, and we heard more of the details, what I heard about it, what really impressed me, is this discussion of trying to see something about the bullets from the distortion of the flag due to the shock wave of the bullets. And he spent some time discussing it, and he was very happy during the talk to be able to exclude that as a possibility, which I thought was marvelous. He was as happy in his mind of knowing that that's not the way to go as proving something that was the effect. And I thought that character that I hear in the way he does business is impressive. Now, I talked to Louis Alvarez, I think, once while I was a student. He came to my lab. This is my lab. This is me dressed as a student. I was doing an experiment essentially by myself in the basement of Burridge Hall. This is the apparatus. It was a measurement of the polarization correlation from the decay of an atom. The purpose of doing that was a test of quantum mechanics. It was to see if entangled states behave like quantum mechanics says. Louis Alvarez came to my lab once with a class he was teaching. It was a seminar. He was teaching young kids about experimental physics. He came to my lab. This is the picture Rich showed. I show it for the same reason. The first thing he said was, everybody put their hands in their pockets. If Rich had watched carefully, his hands are not in his pockets. They're behind his back. This is the closest I could find to a picture with his hands in his pocket. He then made some comments about my experiment. You notice it's very big. He says, why is it so big? It's just a tabletop experiment. I explained to him that, well, there's a beam, and you have to intersect that with a source to excite the atoms, and the source for the light was fairly big. So it scaled the experiment. This is a picture of the experiment in those days, and he made a suggestion. Why don't you use 2 photons to directly excite this state? This was a transition from the ground state to a resonance level that you can make with 1 photon. Those are strong transitions. Some decayed back to the level I wanted, and then you got 2 photons out of it. He said, why don't you do this? Well, I think it was in 1931 in Maria Seeloff's thesis where she suggested 2 photon excitations. They hadn't been observed the first time until 1962. It required the laser. To do this, it required a dye laser. The dye laser had only been invented 2 years before, and I explained that to Professor Alvarez. He didn't seem impressed. Well, this is the result of our experiment. These 2 lines are where the data should all fall if something called Bell's inequality is valid, which would have been another explanation of how quantum mechanics works. And you can see the data defies that limit, proving that that inequality doesn't hold in nature. Furthermore, it verifies quantum mechanics. This is what we could do in 1972. 10 years later, Alain Aspect, in an experiment in which he used two-photon excitation, was able to do that much better. I've often wondered about this and whether I should have pursued this. The 10 years convinces me that probably I made the right choice, although Alain got very famous for doing this so much better. Now it's done even better than that. Let me tell you some other anecdotes about how I ran into Alvarez. When I was at Stanford, I joined forces with Alan Littke, who's here, and a bunch of other people from LBL and Stanford to do an experiment at PEP looking for free quarks. And at that time, there's lots of excitement because it seemed like free quarks might have been discovered in an experiment by Bill Fairbank. And in this experiment, which was like the Millikan oil drop experiment, except with levitating niobium balls, this was the distribution of charge on the balls. And you can see there's three groups, one at minus a third and one at plus a third. To this way of doing the experiment, that could be 2/3 and minus a third or any multiple of a third. This seemed to be pretty strong evidence for free quarks. For many years, this data appeared just like this in the particle data compilation. In 1981, I think about that then, I'm not sure the dates again, Alvarez proposed a blind test of this experiment. And he made a big deal out of this. He came and, under the agreement with Fairbanks, typed a number in the computer that didn't allow him to know what charge specifically he was measuring. And then when the experiment was done, he would come back, tell him what the number was, and that would be subtracted from the number he got. The outcome was disappointing for Alvarez and for Fairbank, and I think the number was a sixth. This was, for me, a big revelation, and I've thought about this throughout my career, about how it's possible sometimes for experimentalists with all the good intentions to sometimes delude themselves into believing a result that they might like as the result of the experiment. And you know that blind tests now are very common in many experiments to avoid that bias. Feeling more like somebody who intruded on various things, I had been to Alvarez's Monday meeting a couple times when I was a student, and when I was at Stanford, Sherwood Parker suggested, let's go down and see the meeting this week. We did. The speaker was a young man. He introduced himself as Walter Alvarez, and he proceeded to give a talk about Gubbio, where he was doing research and this strange layer that he had found. And that was the initial discussion, as far as I know, Walter can correct me, of this whole business about the extinction of the dinosaur. I remember that Alvarez was interested in determining how long it took for this layer to form, and he had this idea that meteorites, if I've got those right, I forget what they're called when they're in the air, coming at a constant rate would produce impurities that aren't normally found on Earth, and that distribution could be used as a dating, and you could see how long it took to put down the layer. We'll hear more, I'm sure, about this in detail. Finally, let me just mention one other thing. For a time at Stanford, and after that I got interested in neutron experiments that I did at an exquisite laboratory in France. At the time when Felix Bloch learned I was doing these kinds of experiments, he told me about an experiment he had done with Alvarez. He gave Alvarez great credit for this experiment, which is really a marvelous experiment. It was a measurement I think, the first direct measurement of the G factor for the neutron. Almost unimaginably difficult with the techniques they had available at the time. And I remember Bloch basically said, without Alvarez, I couldn't have done it. Some years later, Alvarez gave a talk at this meeting in Washington that I happened to be at, in which he gave essentially all the credit to Bloch. This was a rare combination of talents. They reproduced and developed most of the atomic beam techniques that Robbie had already gotten credit for, and they reinvented or invented it for the first time. I'm not sure exactly how it turned out. But this, in terms of what I learned, was not a paper I would have read because it was in the 40s. And the techniques had gone well beyond that in terms of what you could do with cold neutrons. But this was a marvel in experimental physics. Thank you.